Our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids, math, science, history, unraveling the mystery that all started with a Big Bang.
Good morning everyone and welcome to Physics 102, Physics of Sound and Light. We're going to take the opportunity today to learn about the Tesla coil from Brian Carpenter. Brian Carpenter has been with our department for the past 30 years, well 30 plus years, right Brian?
Yes.
And Brian will be retiring in 2 days. So please take the opportunity to ask any questions that you may, because Brian has lots of information to share about this unique apparatus. Thank you.
So did anybody look up to Nikola Tesla?
Mm-hmm.
No? I guess they're one guy. I guess.
Yeah.
Well, Nikola Tesla, he was the fellow that gave us our AC system that we use for distributing electricity. And he was what really sets him apart from other inventors of the time period was he understood something about resonant frequency. About at certain frequencies, things become resonant. That's both mechanical and electrical. He supposedly built a mechanical oscillator that he said would take down any building or structure just by finding the building's resonance and then pumping the building at its resonant frequency. But where he really shined was with this device, and all it is it's a coil and a capacitor that are operated at their resonant frequency. Now the coil is actually a transformer. It has a primary, which has just a few turns, and a secondary, which has many turns. So the voltage gets stepped up. And then when the primary of this device and these capacitors form a resonant tank circuit that then gets pumped at its resonant frequency. And the way we change its frequency is we take the voltage, the high voltage, off this input transformer, and we chop it up using this rotary spark gap. Now, I realize that no one can really see that down there, but it's like the distributor of a car, but instead of distributing the spark to different spark plugs, it simply turns it on and off. As the contacts line up, it arcs across it and then and energizes the coil, and then when the contacts are not aligned, the arc stops and the coil then de-energizes. And for this particular unit, we control the frequency that we're operating at using this dial. And long ago, there used to be a chart that told us what number gave us what frequency, but it's been lost to time, I'm afraid. And then we control the current going to the primary using this dial. So the area, we drag it down to the area there where we're near the Chester building. In the parking garage, we have a fairly tall ceiling. Not necessarily lower parking, but there's a spot where lower parking and upper parking come together, and it goes out to the back. And we plugged it in and started working with it. And at first, we found out we had too many turns in the primary, so we had to take a hacksaw and cut this off and relieve a couple of the turns of the primary. And then, actually, after that modification, it started working great for us. And we were able to jump sparks we were able to jump an arc 2 meters to a test stand. So that's quite a bit of voltage. Go ahead.
Brian, what was the point of the Tesla coil? Just to generate?
Well, no, Nikola Tesla wanted to send us one, but unfortunately it's highly inefficient. And that's why we're not using it. Go ahead. Oh yeah, they get their power from the transmitter. Absolutely. Early crystal radios definitely were powered by the transmitter itself. But you realize they don't require, they didn't have a loudspeaker. You had to listen to it with phones because it didn't have a lot of amplification. In fact, it had no amplification. They don't draw a lot of power. If you wanted to operate your electric drill or your air conditioner, you would need quite a bit more power. And that's where this system unfortunately breaks down. Now maybe they didn't envision all of the appliances that we would have today and all the things we would have to plug in. In those days it was pretty much lighting. there weren't too many other things that they had to power.
What was the voltage that you got this Tesla coil?
You know, for a 2-meter spark, I mean, you can do the math. It had to be it had to be over 500,000. It had to be over 500,000 in order to do that. And actually, there's a picture up here. Do you want of it jumping? If you ever want to, this is always here. There's one on the other side there too, so you can come and look at it if you wish.
Does anyone else have questions for us? Anyone want to ask anything more about the?
Yeah. How many amps was it running at? You know, now it draws 30 amps. Okay. When it's in full operation, we're drawing 30 amps, but due to inefficiencies in the system, the resultant current output is probably a lot lower. You know.
Do you also know how many turns are on the secondary?
You know, I used to. Because we had to count them on. You know, and because we wound that coil. Actually, this is a wooden form that the fellow that built it, Mark Fultars, he made a wooden form. You can't use any nails in it, so everything is glued and pegged together. And when we set this form up between 2 sawhorses, it was really easy to lift. And then we wound all these turns on there, and then we went to go lift it off the sawhorse and realized it was a lot heavier. It was really tough then getting it upright and getting it on the stand by just with the 2 of us. But you know, I used to know how many turns was on there, and I just don't know anymore. But you know, to construct a Tesla coil, the important part is the resonance of the primary with the secondary, and the primary with the and the capacitors that use for the tank circuit. The secondary is simply we're just simply stepping up the voltage. You know, you have so much voltage on this, and then you have so many turns per volt on this. So it's just a giant step-up transformer with the primary operated in a tank circuit paired with a capacitor at its resonant frequency. And the way Tesla did that was to use a rotary spark gap. Today it's possible to do it using solid state. You know, we could drive it at a frequency that it likes. This particular one it's 650 kilohertz. That was considered high frequency in the day. Go ahead, young lady.
I'm Tara Pepper from the physics department. I'm the lab manager, and I'm the instructor for Physics 102.
I'm Brian Carpenter, the electronic technician for the Department of Physics. And I'm Josh Moreno, one of the students in the physics class 102.
And what is your major, Josh?
I'm a major in film and digital media and with a dual major in engineering.
Brian, we're going to ask you some questions about the Tesla coil. So if you could let us know how you power this up and what the various parts are, and as we go on the ask.
Well, this is the main power panel right here. Just love tile floors, don't you? There we go. It's stuck in this now roof. There we go. All right, close that. All right, these are the wires. These are the wires that we hook up to this thing. Here, this is the one that goes to AC power. It normally has a plug on it, but I cut it off. So that don't want anybody hooking it up without me being around, because I got it that way. All right. And this is the cable that goes between the control panel. This is the cable that goes between the control panel and the Tesla coil itself. We got the.
Where does that plug in?
These plug in here. It doesn't actually matter which one you plug in because it's AC. And then this goes on here. That's what actually drives the motor. This is the motor drive, and this is the control, or this is the power that goes to this. This is the power that goes to this transformer. This is 120 volts. 120 volts of this transformer. Whoops.
So Brian, I'm
See, this mounts right on here like this.
And that's AC power going to the transformer. That's AC power
to the transformer. This is DC power to spin the motor, to spin the spark gap motor. There we go.
So the
And that's
white,
all.
the
Now
white
it's
cord
now
is
the control
DC.
panel, right? The what's that?
The white
Yes,
cord
it
is the
is
DC.
right?
And it's getting its DC from here?
That's
from,
correct.
From this?
Well, it's getting it from, actually, it's getting it from, oh no, it's actually getting it from this. Now, there's AC going into this, but it's a DC motor. But what we're changing the voltage and what we're rectifying it. There's a rectifier on here somewhere. There's a rectifier in this panel here that rectifies that to DC to spin this motor.
So when you're plugging it into the wall, then that power splits off to AC.
Right.
And a separate
That's
section
right.
for DC.
That's right. There's a this actually goes to the wall.
That goes to the wall,
Right.
which goes into this box. Can we open this box?
Sure we can.
Okay.
Okay, that just contains the fuses for the input power.
What are the fuses rated at?
The 60 amps.
6.
I had to look. I don't know. 60. It only draws 30. 30 is the most it should draw.
Now, this AC comes into here, goes through these fuses, and then from the fuses comes out over here
That's right.
and up here?
No, yes, it does. It goes to multiple places.
Okay.
Because see, we're applying like the this is a it's an auto transformer like those ones that we use for the it's just a big one. I don't know why, but I suddenly can't remember what it's a power stat. It's a I can't remember what it's called.
It's okay.
No, it's not. Now we know why I'm retiring. The the auto transformers that we use for the spectrum tubes.
Spectrum 2 power supply?
Yes, here this grid.
We use the
rotate
transformer,
right,
an
it's
auto
an auto
transformer.
transformer. What's it called? It's called a variac.
Variac.
Oh, jeez.
Variac.
This is just a big variac. This is also a variac. And the output from this one controls the voltage to the spark gap motor. The output for this one controls the voltage to that transformer.
Okay, say that again. This is the output voltage to the
spark gap motor. It controls the RPM of the spark gap motor.
Okay.
And this controls the voltage supplied to that transformer.
The transformer.
Right. So
Which is giving the current to the coils.
That's
bringing
right.
The current to the coils.
Right. Well, it's bringing the current. First, the current goes to this transformer.
And that's
the
stepping
120
up.
volts is stepped up to 7,200. 7,200 volts.
Okay.
Okay, now one side of the transformer is grounded to this. Oh, also there's a ground line. I forgot about that. We have a ground line. Oops. We have a ground line here that hooks up to.
What does that connect to?
Ground.
But does it connect to this box?
No. Here. Oh, I have to remember exactly where this goes. It could actually connect to any grounding point here. I'm not sure where we used to actually stick that. It's been a while. But one side of the ground wire goes over here to this. This one side of the ground wire goes to this, and the other one goes over to here. I don't quite remember. Here's a bonding strap here. I don't remember where exactly on this that we used to attach the ground.
Okay.
It's been a while.
But the importance of the ground, what is the importance of the ground, Brian?
Oh, well, that's that's how one thing is safety.
Okay.
This part is a ground potential.
Okay.
And then all the AC the hot is on this other side, and that goes to this bank of capacitors, and it goes to the spark gap.
So that's the spark gap.
That's the spark gap. As this rotates, you see the contacts. You see how the contacts, they line up and then they don't line up. When they line up and then they don't line up. When they line up, it arcs that 7,000 volts. That's enough to arc the 7,000 volts across that, and that essentially connects this to this bank of capacitors. And then this acts like a switch in the tank circuit that turns chops up that 7,200 volts into 650 kilohertz to be applied to this coil. So we're essentially we're applying 7,200 volts at 600 kilohertz to this to a parallel circuit that's these capacitors, these large high voltage capacitors, and this tank circuit, or in this primary circuit. It's actually a tank circuit. It's a parallel. Those capacitors are in parallel with this, with that switch in between them. And it ultimately allows the current to flow and takes it away. It essentially chops it up. And we chops it up at the rate determined by the frequency that this motor, or the RPM that motor's spinning.
So why are you wanting it to chop up?
Well, we have to generate high. See, the line current is only 60 hertz, and we need 650 kilohertz. So in order to, so what we're doing is by spinning this, it takes that 60 hertz and chops it up, and to 650 kilohertz. You know, depending upon, actually it depends on the rotation rate of that arc gap. See, we have to generate our high frequency somehow. And years ago, the most efficient way they had to do that was the rotary spark gap. Now, you could do that with a thyristor today, or with a thyrotron. You know, there are other ways to generate. There are solid state and also gas discharge methods that can be used to generate high frequencies today. But in the past, the most efficient way for them to do it was with a rotary spark gap. Anyway, that's what develops the operating frequency for this coil.
When you say this coil, you mean the red coil or the
Well, the red coil, remember, this is just a transformer.
Okay.
Okay, the most important part is this primary is in parallel with these capacitors, and this switch is in between them and allows the current to. Like we had a stand that allows to create an arc gap between these two. You can just draw a spark directly, draw an arc across that thing about 2 meters. Or if you don't have that there, it just simply produces these tendrils going out, you know, in every direction.
So when you were first turning this on, what safety precautions would you use?
Well, that's why this is long. You need to be at least 2 meters away from that. Essentially, that's why this is a long cable. This is exponentially put way far away from this. Okay, and this is isolated. And the noise this thing makes, like, you ever hear the noises in Frankenstein? You know, it's like that amplified by 10. It is really noisy. And it produces all kind of like that's flashing. You know, this thing flashes. It's real bright. It produces a very bright flash each time it arcs over.
Brian, where's the on-off switch?
That's all on this side. The main power on, main power off. So on is red, because red is danger. Off is green, because green is safe. So this is main power on. Now at this point, these lights will light up, showing that you have, I don't remember, these are actually power to each of the circuits that are necessary. The motor, and the main power, the motor, and the primary. Okay, and then you rotate this and bring the spark gap up to its operating RPM. Okay, and then you turn this on, and now you've applied power to the primary.